Alright, so what did we do last time? For a smooth K3 fibration, so when you had a situation where you had a K3 fibration where the total space was smooth and the fibers were smooth, we constructed a certain DT theory of these things, and we also showed that the generating series of these DT invariants of X with a fixed, with some given Chern character where the sheaves were torsion. This was given by some vector valued modular form. This was a vector valued modular form. This was the generating series of Nodal Lefschetz numbers, which was keeping track of, for a fixed cohomology class beta. So you would fix a cohomology class in the ambient threefold, gamma. And you would like that gamma to come from vertical fibers. So there's an embedding of homology of curves on the fibers into the homology theory of X. So you would fix some gamma whose Poincare dual comes from some push forward of some Poincare dual of some homology class on the fiber. And then, so there's, after fixing that beta, we discussed the moduli space of Hodge structures. So for every fiber, there's a moduli space of Hodge structures, and the whole fibration does come with a moduli, pi relative moduli space of Hodge structures. So this is the map pi. And inside that pi relative moduli space, we have these Nodal Lefschetz divisors, which were kind of telling us the locus where if I fix a curve class beta, there's a locus inside that pi relative moduli space whose points are just 1, classes. And then we also saw that there is a map from the base curve C to that moduli space and intersects this locus. And the intersection number was basically telling you, roughly speaking, in a given fibration, K3 fibration, how many of the fibers do contain 1, classes. I fix a beta, but I don't know how many of the fibers do contain it as a 1, class. And I know the Lefschetz number actually tells you that. And then, by changing the curve class beta, we can construct a generating series of these numbers of how many fibers do contain that class. And that's the Borcher's theta function. So this was the Borcher's theta function, keeping track of Nodal Lefschetz numbers. And in the denominator of this thing, we had the discriminant Costerville form, which was something like q n bigger than 0, 1 minus q to the n, to the Euler characteristic of the K3 surface. And this thing is a scalar modular form, scalar valued modular form of weight 12. So this is a modular form of weight 12, and this was a vector valued modular form of weight 21/2. And the whole fraction would give you a modular form, vector valued modular form of weight minus 3/2, which was precisely prediction of a string theorist which discussed this generating series of D4, D2, D0 branes, wrapping these fibers in some ambient background, threefold background, and who actually conjectured that they're generating series of kind of a Mach modular form.
Just a quick question. So what is the parameter in Borcher's theta function? What is the parameter?
The parameter is the curve class.
Curve class.
Yeah. Yeah, so I could have written much more about these theta functions and these cuspidal forms and so on. I could cook it up in a way that you could see, but I didn't do it. Okay, so now let's do nodal K3 fibrations.
Can you repeat a statement? You just mentioned about deep brains.
That's right.
What is the statement you just mentioned?
So the conjecture comes from a string theory where they are considering some D branes where the D brane data is, if you like, is the D4, D2, D0 brane. So you have D branes wrapping the fibers of this K3 fibration over the base, where the D4 brane charge is some R times class of the fiber. I call it class F. The D2 brane charge is given by these cohomology classes beta or gamma after pushing forward to the threefold, and D0 brane charge is given by the churn character of our sheaves. And there is no D6 brane charge because our sheaves are torsion. So now we would like to do the same thing for nodal K3 fibration, and the lecture today is kind of, from technical point of view, it's interesting. Because it gives you a way of analyzing these things too, and later when we discuss the same statements for Kupo-Kumar-Bafa invariants and stable pair invariants, again, Conifold transitions and so on come into the picture. So let's discuss a little bit about nodal K3 fibrations. So let X be a projective non-singular threefold, and the morphism let's call it pi again, X to C be a smooth except at finitely many fibers. The smooth fibers are K3 surfaces. Okay, and the singular fibers are non-singular K3s are given by, maybe I write it like that, are contractions of non-singular K3s at finitely many minus two curves, and therefore, is what does this meant is that therefore finitely many fibers can have ordinary double point singularity. The idea is that, you can also consider fibrations where the K3 fibers can have rational double point singularities of general type, and then more general type, and then using deformation equivalence, you can always argue that rational double point singularities are deformable to ordinary double point singularities, and therefore, if I started with a K3 fibration with RDP singularity, I can always deform it to one with ODP singularity. And the theory of K3 fibration with ODP singularity will suffice because these are deformation invariants that we're calculating. So it captures that too. But you need to have, for this particular Conifold transition precision, you need to have ODP. So,
conjunction -2 is the A1 singularity.
Yeah. Now note that in this case, canonical bundle of X is coming from the base, some bundle K, I called it, for some K in Picard of S, and we assume that churn character is again, churn star, is given by 0 R times F, gamma, and churn 3, which was some element of I from 0 to 3, h to I, rational cohomology of X. These were cohomology classes giving us the Chern character where F is the fiber class. F is the class of a fiber. Okay? Okay, so we have this situation, this setup, and now we can make an assumption. Assumption is that we assume that the Chern character vector satisfies the condition that by the way, maybe at some point, if you could kindly see if they come back when the door opens, we can get some batteries. You think? Somehow, when do they come back? Like come to the office, Sarah or someone else? Maybe, can you check like in 10 to 15 minutes from now? You know, it's a good workout, but alright, for now I'm okay. So we can assume that the Chern character vector satisfies the condition that R is equal to 1 from now, and for all F with Chern of F equal to Chern of a star, we have stability, physical stability is equal to, well, we have semi-stability equal to stability.
So you're in rank 1 over a support.
Yes. Now we have honest rank 1 over the support. You could have a stable shifts of rank 2, rank 3, but in this particular analysis, we run into issues if the rank is not 1. Over nodal K3 fibrations. Over smooth fibrations it was okay, as long as the support of the sheaf is reduced and irreducible. Could have higher. Okay. So now let S1 to Sk in X be the singular points of the fibers of X over C1 to Ck prime in the base curve C. So what is the situation? We are looking at K3 fibration like that, and we have singular points S1 all the way to Sk like that, and the base of where they happen is C1 to Ck prime on the base. If K prime is given is an even number, is even, we define C0 equal to C1, and if K prime is odd, we define C0 to be a generic point of an arbitrary point of C arbitrary point of C, disjoint from. We want this number of points on the base to be even. If the number of fibers over which we have nodes is even, no problem. If it's odd, we add a point, we make an even number of points, because later we want to construct some sort of 2-to-1 ramified cover of the base curve. That's what we want to do. We want to ramify over even number of points. And define C0 to be an arbitrary point of C disjoint from C1 to CK prime. That's some technicality about the geometry of this thing. If you want to get eventually some sort of, smooth K3 fibration, that's what we want to do. And okay, and now let epsilon be from C tilde to C be a double cover of C branched over the points C0 to CK prime. So what we want is that the fiber product, perfect. Yes. Let's just see. Oh, that's great. Thank you. Where did you? Oh, thank you so much. So let me just. Is this? Thank you. Yes, those are, yeah. Yes. Much better. Right. Thank you so much. Yes, this is much better. Okay. So if you have the situation, the fiber product, then the fiber product epsilon pullback of x via this map is a threefold. Remember that we are assuming that the original threefold has ODP singularity along the fibers, and now I'm pulling this back, and I can so look at what happens to the equations defining those nodes. They become conifold. So it's a threefold with conifold singularity. Singularity is exactly at the inverse image of our points, which I call SIs. SIs. Okay? So now let x tilde be the small resolution with exceptional non-singular rational curves, exceptional locus. If it is a small resolution, it has an exceptional locus. So non-singular rational curves, I will call them again E1 to EK prime, and let EK, E1 to EK, and let pi tilde from X tilde to this curve C tilde be the induced morphism. So what's the picture?
So presumably it's only a small resolution rather than the small resolution.
A is small resolution.
That's
That's right.
many.
Yeah, it's A is small. Yeah.
So you have many, and
Yeah.
you just choose one.
Mm-hmm. To kind of blow up X along the kind of, what to say, one-dimensional subschemes that pass through those singular points, conifold singularities of the pullback of X. That gives you some ideal, and you blow it up along that, and you will get this a small resolution, where for every one of those conifold singular points, you will get this rational curve, -1 curve over there. So this is what is happening. So you have C, you start with C, and you're pulling back this C via you construct a ramified double cover of this curve C, and this was your X, and you look at the fiber product like that, and then you look at the small resolution like that, and this induces a morphism pi tilde.
Somehow, I'm not sure it's related or not. Somehow this probably remind me of some lecture I heard about Strong-Yang-Zaslow mirror symmetry construction.
Really? Okay. They use this is precisely conifold transition.
I mean this is small resolution.
Well, I don't know. I mean,
small resolution stuff.
It's possible. I mean, I'm not really. I don't remember exactly.
Song was here before you came, and he was now at Brown. You do symplectic geometry.
It's possible. I mean, this is very kind of a classical method of resolving such singularities. I mean, yeah. I mean, and it was actually also invented, kind of, or in geometric engineering and so on. It has been ever since, I don't know, 40 or 50 years it's been used. So it's not some new thing. It's just you have this threefold with such singularities along the fibers, for example, and you transition to a smooth fibration by passing through a threefold with conifold singularities. That's why it's called conifold transition. But yeah, you're right. I mean, it should be all over the place. I don't know exactly where it was used. Yeah, maybe in this YZ also. I don't remember. So the normal bundle of these exceptional locus, the normal bundle of elements in the exceptional locus, EIs, in X tilde, is isomorphic to. So these are -1 curves. So these are rational curves, so it is isomorphic to something like that. And moreover, now you can do also something else, which is, this is one way of getting a smooth fibration out of this. We want to do something else also, another thing. So this is the other threefold we want to construct. So let this time E of t, or I call that epsilon, so maybe epsilon of t, C of t to C be a double cover of C ramified over or branched over branch at, let's call these things C0 of t, ck prime of t, generic points of C. Points of C. So when so what is it we are trying to do? You see, we had this fibration C0 to C of k prime with the fibers on top of them, and these were SKs. So one way of smoothing this thing out is basically by this Conifold transition, which I just explained, and we would like to construct another threefold as well, which is for every one of these special points on which the singular fibers happen, we would like to look at the generic point. So this one I call C0 of t, this one I call ck prime of t, and in the limit of ci of t, when t goes to 0, will be just ci's. So we would also construct the double cover of this curve ramified along these generic points, and we get another threefold. And by comparing these two threefolds, eventually we would like to kind of relate dt theory of the smooth fibration to the dt theory of the original nodal fibration. But let's just do this slowly so that we can see what's going on. So for now, this geometric construction, we have this thing, and generic points of C when t is not equal to 0, and C of 0 equal to C when t is equal to 0. Right? So this is about this ramification.
But there's something puzzles me. I thought you originally go through this is because of the fiber singularity. And
yes, right. I mean, you see.
But all the other fiber singularity is still there.
Right. I mean, the thing is that
what's the purpose?
Goal is that you would like to. Okay. I mean, the purpose is that this is just. I mean, this gives you a threefold fibration on the base curve when in the limit exactly gives you the nodal one. That one is the smooth thing. So somehow I would like to construct two fourfolds. That's what I would like to do. I would like to construct two fourfolds as degenerating families over A1. The generic fiber of one fourfold over the generic points of A1 gonna be my x tilde. And the generic fiber of the other fourfold over t not equal to 0 is going to be xt that I get from here. And then what happens is that over the special fiber of that fibration is going to be, again, some smooth thing, some normal crossing of a smooth thing with something else. And the special fiber of the second one will have x0 in it.
But you mentioned for that extra parameter is a t or something else.
Yeah, we will see. You will see now. Yeah. So I will show you how to construct fourfolds. You see, you want to find a relation between x0 and x tilde via degeneration technique. Okay? And so this is the procedure.
Degeneration technique.
Yeah. It's complicated, but I will show you. So
not obvious because usually degeneration technique, you want to break something to original stuff. What you really want to do.
That's right. That's right.
But what happens here? I didn't see.
You will see.
Oh, I'll see.
Yes. And let x of t be the epsilon t star of x. Same as before, but this time we call something else x of t. Now we would like to relate to relate x0, xt, and x tilde to each other via degenerations. Okay, so we start with good degenerations. Good degenerations, which I will call R1 and R2. R1 I would like to define as blowing up x tilde times A1 along these locus of these rational curves, E1 to EK times 0. And I would like to have a second degeneration, R2, which is basically just blow up x of t along these points. Let me see. S0, so S1 of 0 to Sk of 0. You see, as soon as I'm pulling back x, so where, let me just say where, okay, Si0 is the limit when t goes to 0 of SITs, where SIT is the preimage. SIT is by definition just the preimage epsilon t inverse of Si on the original variety. SIs are nodal points in the fibers. Then I look at the ramified double cover of the base curve C. I pull back the whole thing. I look at the preimage of these points over there. I call them SIT. But in particular, when t goes to 0, I will call them Si0. So if you ask me, for all values of t, what is this thing? This is a fourfold. This is a fourfold. And this is a fourfold too. So let me write it down.
A question. So, in the original K3 fibration with singular K3 fibers, over that singular point of fibers, there's always a local section.
Why are you asking?
Because you need the SIT, right? That means
That's right. Yes.
So they always.
Yes, of course.
I'll take it as a
Yeah. So the way I want to look at it, if this is the affine line, and in here we have this parameter t of the affine line, and in here we are actually looking at this affine line itself. On here in affine line, this is the fiber of R1 restricted to t not equal to 0, if t is the parameter of the affine line. This is just x of, okay, so should I write it down? This is just x tilde. And what happens is that you're blowing this whole fourfold along here. So the fiber over here is just something I would call fiber over t equal to 0 is some normal crossing y union. I will explain what these are. d1 to dk, some projective space p1. And fiber over here, R2, t not equal to 0 is x of t. And in here, R2, t equal to 0 is something, again, y union d1 to dk, p2. And now I need to tell you what's the structure of these p1 and p2. What are these things? Okay, so the idea is that here, y, it just comes from the geometry that y is the blow-up of x0 among S1 to Sk. And it's in common between the both of them. And then di's are isomorphic to P1 times P1. And, well, you can also basically say that these are projectivizations of OP101 squared. And P1 here is projectivization of O of P1 plus O of P1, 1 that. And P2 is just, turns out that P2 is a double cover of P3 branched over a smooth quadric surface, a smooth quadric surface, which is isomorphic obviously to P1 times P1. So P2 is just a smooth quadric in P4, right? So it's a non-singular quadric in P4. And well, you know, these, maybe I should add a remark, and these two degenerations, they have names. Again, they come from previous constructions, and we're happy that they existed before we needed to invent them. So maybe a remark. I mean, who knows what is this degeneration? This kind of, you should know. You might realize it. You might realize it easier. This is just a degeneration to the normal cone of those EIs. The rational curves is the degeneration to the normal cone of those. So remark, the first degeneration whose total space is the fourfold I called R1 is the degeneration to the normal cone, is the degeneration of X tilde to the normal cone of EIs, the union of EIs. And the second degeneration R2 is just something that was, I think, worked out for the first time by Yao and company. Is nothing but it's called. I'm not sure though about that fact. If for the first time it was worked out by this group, but it's called the semi-stable reduction. Reduction of a Conifold degeneration. That is what they called it. In which the i's which are inside y is attached to a smooth hyperplane section H I in the ith copy of P1, ith copy of P2. Okay? So I should have maybe, so somehow, so maybe I should also write in here that we have ith copy of these things, P1 i's, and we have ith copy of these things, P2 i's. I mean, the reason that we have ith copy is that if you have one rational curve, you can degenerate the whole threefold to the normal cone of that one rational curve. The special fiber of that fourfold will be blow up of your original variety x0 at those singular points, and a cylinder. This cylinder, it looks like, so this guy looks like something like this. If there were only one rational point, this will be the projectivization of O of that curve plus its normal bundle, conormal bundle, of E1 inside, in our case, would be X, right? The normal bundle of, conormal bundle of this thing is OP11 plus OP11. And this whole thing is, it's like a cylinder, and it has some infinity section and it has some zero section. Infinity section of this thing is precisely the infinity divisor inside here. This is basically just projectivization of OP1 of 1 squared, which I call D1. And this threefold is attached to this other threefold along D1. But if you have multiple EIs, multiple rational curves, you have multiples of these things, right? So you have rational curves of E1 to EK, and you have multiple copies of this, P1, I can call them P1i's. And you have multiple copies of these divisors, I can call them D1 to DK. Each is given by blowing up E1 or EI the way we did. Okay, so these are basically P1 times P1, quadric surfaces that we get this one. Same as here. This is a different blow-up construction, and you get multiple copies of these, here's the surfaces, and they're attached to hyperplane sections of multiple copies of some double cover of P3. This is just geometry. Anyway, so out of these two things now, you've constructed two fourfolds, whose generic fibers, one of which is xt, one of which is x tilde, and whose the special fibers have the nice property that they are given by normal crossings, where one side of the normal crossing is the same for both. And that's the blow-up of our original variety along with singularities. But these two things, well, they are different. Okay, now our procedure is to kind of look at degeneration, Junli's degeneration technique, Livu actually, for DT invariants for these fourfolds, degenerating families. But I mean, I needed to give you detailed information about these underlying geometries anyway. We could have as well just omitted all of that, but since it's a lecture, I thought maybe I should do it. So now digression, so goal is, maybe first goal, to relate DT theory of x tilde and DT theory of xt via degeneration. Techniques of Livu. But before that, I need to tell you a little bit about these relative moduli spaces and so on.
I have a quick question here.
Mm-hmm.
So far you're dealing with only the manifold, how to resolve, for example,
That's right.
etc. So no behavior sheep enter.
No.
So then, but then if you want to use Liu, assume you also take.
We will. Now it's a. I need to first lecture on Liu. Yeah, that's right.
Oh, you are going to.
I'm going to. So now digression. Relative moduli spaces. So, at least roughly speaking, in Gromov-Witten theory, this starts from work of Julie, where we were trying to count stable map invariants inside a given threefold, and we didn't know how to do it, for example. We didn't know how to count them, and we would generally constructed this beautiful machinery of degeneration technique where he would take the underlying variety, underlying threefold in this case, degenerate it into a normal crossing variety such that the total space of this degeneration is a smooth. That's what it means, a good degeneration. And so then he would ask, what happens to the curves I would like to count? So the curves also degenerate, and they will become curves like this and curves like that. And then on each one of those pieces, maybe he calls them y1 and y2, he invents the kind of defines the notion of relative curve. So that means that some curve which is still stable with the stability condition for a stable mass, but it also has some relative profile along the relative divisor that you get this way in this degeneration. So he will call these things curve C1 with the profile E1, curve C2 with the profile E2, and then he would say the count of a stable mass in here, like basically Gromov-Witten theory of curve C, is basically just given by product of the relative Gromov-Witten theory of C1 with the relative profile E1 times Gromov-Witten theory of C2 with relative profile E2, comma, E2, as long as there are compatibility relations between the two curves. And that compatibility relation is exactly the relative profiles along the relative divisor must match. So compatibility, which in, roughly speaking, at least in this notation, E1 is the same as E2. So in order to do that, of course he needed to construct a moduli space for which every point is a curve with some relative profile along this relative divisor. He called these things relative moduli spaces, and he needed to actually show many things, so much detail like these, how to construct these relative moduli spaces, how to define them, how to parameterize curves with such property. Are these moduli spaces compact, proper, separated, or not? So that's why it's a beautiful machinery constructed by him. In this particular example in here, we are trying to do the same thing, however, for sheaves. You would start with sheaves. Okay, so this is a threefold, but it's really a K3 fibration. Now we have constructed two smooth K3 fibration degenerations. And for each one of those families, I have stable sheaves in here. First thing first is to relate the T theory of the generic fiber of every one of these degenerating families to their special fibers. And then I'm going to, at the end, use the fact that there is a piece in common between the two. And somehow, if I show that this guy and this guy do not contribute to my DT theory, then using a formula like that, I can say DT theory of this is relative DT theory of this with respect to the divisor, relative DT theory of this with respect to the divisor. Same as here. If these contribute nothing, DT theory of the generic fiber is related to some relative DT theory of Y, which is also in here. So the generic fibers of these two things are related to each other. Their DT theories are related to each other. And then from here, I can relate this to the original x0 with a very simple kind of calculation, and then eventually x0 and x tilde are related. So this is what we want to do, relative moduli spaces. Okay? But for sheaves, really. So what does it mean, a relative sheaf, for example? Okay, so this is the digression of the. So let Q, this is for now some short kind of review of degenerations of Jun-Lee and Wu. Let Q from W to A1 be a good degeneration of the projective threefolds. That is, first of all, W itself is a smooth. Secondly, all fibers except high inverse of 0 are smooth. Projective threefolds. And thirdly, pi inverse of 0 is some W1 union W2 over some divisor where Wi's are smooth threefolds. And D inside Wi for I from 1 to 2, the relative divisor is a smooth divisor. And pi inverse of 0 is a normal crossing, divisor in the total space of the family which I call W. So starting from here, then we can show that then Lee and Wu construct the Artan stack. They construct the Artan stack of expanded degenerations so it is something, maybe I use a curly W goes to W, curly C goes to A1, and this is the map Q, P, and map R. So what's this Artan stack of expanded degenerations? I will tell you what does fibers look like, where away from R inverse of 0, away from R inverse of 0, the family W tilde is isomorphic to the original family. And so, original family in the following sense to this family. Okay, and the central fiber of the of W tilde over C tilde is given by union over all K of K step degenerations K step degenerations, I will call that WK. And what does the K step degeneration mean? It means that you're kind of degenerating this original variety W into the normal cone of a divisor inside WK many times. So what does that mean? It means that you have W, if you degenerate it, you will get some degeneration whose special fiber looks like something like this. But you do this K many times. So projectivizations of O of D plus conormal bundle of D inside W. And then at the end, you will attach, it's a K-step degeneration of the original variety W. So it's like, at the end, you attach W to it. Like that. So if you really want to know what is this expanded degeneration doing, its generic fiber looks like your variety, or the family of your degenerating variety on an A1, and a special fiber of it is like a cordionic expansion of your variety in the middle, where you just put K many copies of these threefolds. It's like accordionically you expand it. The reason this is an Artan stack, okay, so one thing is that you can ask in the level of the variety, just one variety, what does the K step expansion mean? It's just degeneration of that variety into the normal cone of a divisor inside that variety K many times. That's it. Now you have a family of varieties over A1. So this gives you another family whose generic fiber looks like the original family, whose special fibers, well, they look like these, but they are union over all such K of these things. This is the important part. And it's an Artan stack because each one of these cylinder type threefolds, these are all isomorphic copies of D, and eventually you have your variety here and you have your variety also here. Each one of these cylinders, you can see, right? This is a divisor. This normal bundle inside the original variety is like some line bundle with fibers are given by P1. So each one of these cylinders, they come with an action of C star. And eventually you would like to look at all possible such things up to reparameterizations of the base, which is A1. And so you need to mod out, in some sense, by this action of C star. The C star action is some sort of C star to the K acting on the moduli of such pictures, where the way it acts is that every C star only moves points inside its own cylinder, but it acts trivially on the remaining cylinders. So that kind of defines an action of C star to the K on this, and you mod out the locus that parameterizes pictures like this by that C star to the K, and that's your Artan stack.
So you're talking about shapes, and there wouldn't be a curve, but if there was a curve, where would it be now?
Yeah, so if there is a curve, then your curve gets extended, right?
Yes.
Yeah.
And
Look, why are we doing this, right? Let me tell you why we are doing this.
but you're trying to avoid the curve to flow into the
Exactly. If my curve falls into the
Is
divisor,
there a time, like K, is there a value for K into the
yes. They actually show that this procedure stops after finitely many times of doing it.
Okay, so it's finite. But
Yeah.
But there's not like effective formula or something.
Yeah, when you restrict to stable curves, this procedure stops after finitely made. Why? One reason is probably, I can see it in the sheaf sense. I might have forgotten the Gromov-Witten theory picture. You see, let's do the sheaf sense. I will tell you why this stops, and the curve sense is exactly the same thing. Okay, it has to do with the curves having finite automorphisms. You know, if you have a cylinder.
So it's stable.
Exactly. If you have a cylinder when there is no curve in it, okay, you're looking at curves inside this threefold. This is still a threefold. I could have a curve which is in here, but it doesn't extend over that. Well, okay. I mean, still there are C star automorphisms of those cylinders, and those are not finite. So my curve needs to really be extended in all of them, and there are finitely many times that it can do that. After some time, the curve does not get extended, and you just get an empty thing, and the curve just be, you know. So then over there you have C star automorphisms, and that's not nice. Yeah? Sheaf situation is also the same, and anyway, but this is my naive picture of Gromov-Witten case. Anyhow, I mean, you should also take everything with a grain of salt, so to speak. You should look at it's really sophisticated machinery. I would encourage everyone to have a look at their paper, which eventually actually got published. It's a beautiful paper, and the Gromov-Witten paper was published a long time ago, only by Jun Lee. The one we are talking about here is the Lee and Wu paper.
Where was that paper? Was it JDE or not? This paper?
The Lee Wu paper? I don't think. I think it was in communications analysis geometry. Yes. So now you have this, and together with automorphisms, C star induced from C star to decay. This is what I just mentioned, induced from C star action along the fibers of standard ruled variety, these ones, projectivizations of O inside there. Similarly, hold that. Now, similarly for a pair of smooth projective variety Y and a divisor D inside Y, the Artan stack of expanded degenerations, is given by something like this. So if I have some Y together with a divisor on it, and it is over a spec of C, then I could have some, again, affine, some stack, A1 stack on here, and I can have some Artan stack of pairs like that, expanded degenerations of pairs like that, where the generic fibers of YD are given as the pairs Y and D. given by YD as before, the kind of a family of Y and D over respect of C away from the origin. I didn't give it a name, but anyways, away from the origin, and the special fiber is given by, so if you have Y, it would be given by Y union of D normal 1 over D inside Y, and then that's it. You see, it doesn't have that last piece in it. So you take your original variety, the family of your variety, and you look at expanded degenerations of that family, W. And the special fiber of the moduli space of expanded degenerations of that thing looks like W R many or K many copies of these cylinders, these root varieties, and then a copy of W at the end. The argument is that this expanded degeneration moduli can be written as all possible products of moduli spaces of expanded degenerations of pairs. Pairs of the Y1 and Y2 with respect to a divisor D. So that's how you're doing it. So in the level of just one variety, W goes to Y1 union Y2 over D. And now we want to do all of this in the level of family. So you have a family of such things over a curve, and you have a family of such things over a curve. And so a special fiber of the modulus of expanded degenerations of this thing looks like kind of gluing expanded degenerations of Y1 with respect to D, which looks like that, and expanded degenerations of Y2 with respect to D.
Since your original deformations was just deforming one copy of the B, and I have many copies. So you're looking at some, subspace of the deformation where all those are identical. Right?
Yes. All of the copies of these are identical. That's correct. That's correct. All of these are identical copies. I just repeat the procedure.
Would it work if you have B, which is a higher production subvariety sitting inside?
D, which is what?
Let's say it's not a threefold, it's a fourfold, and you have surface sitting inside, and you want to avoid some curve falling into that surface, and you just blow it like this. But then you got a cylinder piece with higher symmetry, which is not star.
Oh yeah, so if it is not a divisor, yeah.
I mean, maybe the theory is not defined, but
no, I don't know.
Does the degeneration work?
I don't know. No, I don't say. You need a divisor. So, I mean, for this machinery, you need to degenerate along the divisor.
What's the reason?
I mean, I just don't know. That's what I'm saying. I just don't know what happens if you have higher codimension.
Okay.
What happens? I don't know. I mean, the point is that the cylinder could have higher symmetries. And if you prove that you're looking at modulations of sheaves where the sheaves are also stable and somehow you have a way of, you see, or eventually the way that they prove the modulations of curves or sheaves on pictures like this is a DM stack or even a scheme is that they show that when you restrict to sheaves which are stable, you don't see all of the C star to the K many copies of symmetries of this thing, right? If you have more complicated symmetries for those cylinders, fine. If you can show that the stability of your sheaves restricts you to DM stack, then you're in good shape.
You're saying you need to find the right condition.
Yes. I'm saying you need to find the right condition for, as I will just say. So definition of what is the stable sheaf in this case. So now.
Right, just some comment to what he said. I think the case you mentioned, or even the case when D is not a smooth divisor but a normal crossing divisor, I think no one knows.
No one knows.
Know how to,
That's
how
true.
to
No one
extend
knows.
this.
No
But on
one
the
knows.
other hand, there's another different kind of technique. If I from my memory called log. Is that
Yeah.
called
That's
log?
right. That's right.
It seems bypass all this.
Yeah,
It's true. If you're looking at,
I've heard of it.
in case of Gromov-Witten theory, if you're looking at log curves, the log structure of a curve along a divisor tells you the infinitesimal information of that curve when it gets closer to that divisor. And if you construct a moduli space of curves with logarithmic structure along the divisor inside your original variety, that already contains the information of how that curve can fall on inside that variety without you needing to blow up. And actually, I have seen one talk last year in here where actually someone told me from the log structure point of view, he can even tell me, like you see, the faster the, okay, so this is really, really naive, right? This is like high school naive, but the faster your curve approaches that divisor, the more would be the number of copies of these cylinders. And this guy, he actually showed me somehow, I mean, the higher the order of tangency of curve that when it falls inside the divisor, then the more you need to blow up in order to separate it apart from the divisor. This is kind of intuitive. And actually, this guy showed me that from the log structures, he can tell me how fast the curve approaches the divisor, and he could also recover from a very complicated combinatorial formula how many cylinders do you need if you were supposed to use Joule-Lee's construction for the relative moduli space. See what I mean?
Are these talks somewhere in the archive?
The log structure one. Yes, the Chile Chen is the one who is expert on this.
I know I mentioned.
Abramovich, Pantecchi, these people are working on that. So to comment, if you can construct moduli space of log sheaves with logarithmic structures along some divisor.
Gromov-Witten side blocks, that log stuff.
It's done already.
But on the sheaf side, is there a
No, it has not done. I was actually trying it myself. I know what a model for a log sheaf is, but it doesn't work.
Oh, you have a definition of log sheaf?
I can give you a definition of log sheaf. Yeah, it's a parabolic sheaf. It's a quasi-parabolic sheaf. It's a sheaf with a quasi-parabolic structure when you restrict it to the divisor. And then you can construct these moduli. This is no problem. You will definitely avoid bubbles and so on, no problem. But whether or not those numbers that you calculate match with the Liu numbers is not obvious to me. But we can discuss it further. This is one of those things which is really hard, so
can we compactify the Calabi-Yau moduli space nicely, and then the Gromov-Witten invariant can deform smoothly, with this degeneration?
oh,
Look at the moduli space of printing, add on with some normal crossing, and then the Gromov-Witten invariant can go over.
yes, you can do that. Actually, one procedure, I don't know if I understand the question correctly, but if you were supposed to compute higher genus Gromov-Witten invariants of quintic, for example, how you would do it, you would use this strategy of multifold degeneration of quintic. So you will degenerate the quintic into a quartic and some blow-up of P3, and you degenerate the quartic to a cubic and a blow-up of P3, and eventually you will just end up with two P3s meeting along the P2. And the good thing about them is that those are toric projective, and you can use localizations to calculate higher genus Gromov-Witten invariants, and you can reverse engineer the problem back to quintic. But
it's more
very hard.
interesting to look at it as a kind of modular form or something, some line bundle, some Caesar of some line bundle over the total compatible modular space. You look at the Gromov-Witten invariant and all that. You probably put a generating function.
Yes.
And it would be nice to see that is a globally defined modular space compatible. Then you have much more control on those functions. Because now you know how it degenerates and all that, and you hope that it satisfies some equation like the modular form equation, and then you can compare it.
Oh, that's interesting. No, I don't know. I don't think.
Well, if we can do this one, it looks like you should be able to do it.
I see. Okay.
So, in the way you package the Gromov-Witten invariant for hygienists and all that, hopefully.
Oh, okay.
Hopefully, I don't know whether you can, as a some session, some line bundle over the total modular space.
I understand.
And then hopefully you can complete it that way. Because then there are only a few sessions in general.
I see.
And if allow you find the sessions in the other way, then you can complete it.
Okay. I see. Yeah, I haven't thought about this, but it's a good proposal.
Okay.
So because we are at 10:30, I mean, I would just finish this relative moduli space. Probably we would squeeze in, some other section. I don't know, but I will finish this now. I mean, we still have time. So definition. This is due to Li and Wu. Let F be a coherent sheaf. Coherent sheaf on a C scheme T of finite type. Finite type, and suppose that Z in T is a closed subscheme. Okay. F is called. This is the question that Pengao was asking. F is called normal to Z if this condition is satisfied. For 1 of O of T, F O Z is equal to 0. If this condition is satisfied, your sheaf is normal to Z. A coherent sheaf F on k step expanded degeneration of the variety Y is admissible if F is normal to all isomorphic copies of DI, which are isomorphic to the original D for I from 1 to K. Now suppose that nu is a locally free sheaf on Y with respectively on W. I have the pairs Y and D and a W, which W degenerates into Y1 and Y2. And O1 be an ample invertible sheaf on Y. Then Li and Wu tell us what the stable sheaf means in this context.
Sorry, before you erase.
Yeah.
So is there a notion of normal to Z, that Z is arbitrary closed subscheme?
Yes.
Arbitrary.
That's right.
I thought it's alright. I thought this normal is at least in original what is that DM Wu's paper meant to me it's sort of flat along the transverse direction.
That's also equivalent to that.
Equivalent to this.
Yes.
And this notion is for
Normality. This sheaf normality kind of is analog of supportive to sheaf to be transversed to the divisor.
In these papers, the concept seems to. Here, I'm just thinking if the Z is very, very bad, and then what is the notion of?
Well, the Z is not, at least in this situation, the Z is not bad. It's a smooth divisor, right? So.
In a
Yeah,
true application.
and in their application as well.
But this notion for arbitrary is.
Oh yeah, well, okay. This is, I think, their definition. I mean, I don't know. I mean, it is a definition of the word normal, but whether or not you can translate it to transversality of the support or not, yeah, it's a good question. So this is that, and then so Li and Wu construct the code scheme. Code schemes code nu P Y mod D, respectively code nu PW over C of quotients. C is that of quotients this phi is, why do we need a locally free sheaf? We are constructing quotients, sheaves as quotients. So P upper star of nu to F on YK, or respectively WK over C, where first of all F is admissible, so F is normal to all of the isomorphic copies of the divisors that you see in this accordionic expansion of your variety. And secondly, phi it has finitely many autos covering covering the automorphisms C star to the K. And thirdly, you see, this is what restricts your Artan stack of sheaves over these. Okay, so you have the moduli space of expanded degenerations of a variety, that's an Artan stack. Then you have the moduli space of sheaves over this expanded degeneration, and when you focus, you restrict to the stable locus, suddenly it becomes a DM stack because of finite automorphisms. 3, the Hilbert polynomial. The Hilbert polynomial of F with respect to pullback of O of 1 is P. Okay. So, okay, so we need more kind of next session. I will go over these and I will just write down the final degeneration formula, and then we move to the stable pair degenerations. However, let me just, for those of you this is important, right? I mean, you need to know, at least understand what does this degeneration do, right? The idea is the following. So let's say I give you a surface. Surface is a good example. So let's say I give you a surface S with some divisor in it, with some divisor D in it. And I would degenerate the surface to the normal cone of that divisor. It becomes something like this. And this is the projectizations of O plus normal cone, normal bundle of divisor inside the surface S. And let's say I'm interested in moduli space of ideal sheaves, relative ideal sheaves on here. So I look at the ideal sheaves of points in fact. So let's my F be by definition, ideal sheaf of bunch of points, and I would like to construct a moduli space. So goal is to construct a moduli space where I of np, moduli space, where I of np is normal to D. You want to construct that. What does that mean? It means that Tor 1 over OS modules of ideal sheaf of this many points with respect to structure sheaf of that divisor, you want that to be equal to 0. In other words, if you're looking at the canonical short exact sequence of this divisor, O of S minus D goes to O of S, goes to O of D, goes to 0, and you tensor with this with the ideal sheaf, then you would like basically to have, by tensoring, you would like I of ideal sheaf, I of NP minus D to I of I. You want this map to be injected. That's what you want. Okay. What happens with respect to geometry? If you look at the co-support of these ideal sheaves, this normality, sheaf theoretic normality, literally translates to transverse intersection of the co-supportive ideal sheaf with that divisor. And the question is, what's the transverse intersection of a point and a curve?
Sorry, you made the term like co-support?
Co-support, because the ideal sheaf is the sheaf of functions vanishing on some things. So the co-support is the points. Right? Co-support is the point. Okay. I mean, you can also do this with the structure sheaf. I mean, a skyscraper sheaf of these things, no problem. Okay. Now, okay. So what's the transverse intersection of a bunch of points with a curve? What is it? Transverse intersection of points with a curve is what? Transverse intersection of two curves is something like this. Transverse intersection of point and a curve is no intersection. As simple as that. Otherwise, I mean, how do you, right? So you would like to think about the situation where if your points are infinitesimally deforming to this divisor, you would like them not to lie on that divisor eventually. Right? But they might be. As you're degenerating your family, you're looking at the perturbation of your ambient surface. Your points are also being perturbed. These are given by functions. And it might be that your point, I mean, by the way, I could degenerate the surface to anything else also. S1, S2, and D. As I'm degenerating my family, the points could also degenerate, and some of them can fall inside here. And if they fall all inside there, they would not satisfy this condition. So what should I do? I should look at this degenerating family, which I can call the total space of which I can call Y1, Y. And I can basically blow up Y times A1 along the divisor times 0. Degenerate Y along this divisor. So basically the question is, you would not like to see a picture like this, right? So in the Junli and Wu, or Junli himself did a picture, he would separate these things apart, S1 and S2, and he would like to say, how can I replace S1 and S2 and these pictures? What should I replace it with so that I don't see these points on my relative divisor? So he does this thing twice. He does it for S1 relative to this divisor. He does it for S2 relative to this divisor. So he takes S1 and degenerates it into a normal cone of S1. So S1 is now over here. He gets a family. Again, the generic fibers of the family are where points are not sitting inside that D. The special fiber of this family is S1, D, and this normal cone of D inside S1. We can do only one of them, but the same picture holds for the second one. And so what happens is that every point of D will be replaced by some P1 fiber, which is a stretch in the normal direction to that D. and this is the cylinder, so these are the P1 fibers. And of course, what happens to these is that they will be sent somewhere in here. But it might be that I have maybe 3 points, and maybe the third point fell in here. And this is the zero section of that root variety, and this is also isomorphic copy of D. So you don't solve the problem. If that's the case, you will again take this thing and blow it up, degenerate it into the normal cone of this guy. And eventually you just do this finitely many times, and you get a picture like that. And eventually you can make sure that your points are just not lying on any divisor. But then the Junli's machinery does not guarantee necessarily that maybe you may get cylinders which are empty, there is no point in them. If you have a situation like that, these cylinders with no points on them, they have C star automorphisms. And the sheaf, which is inside here, will not be stable in the sense of Junli. You need to have finite autos covering the C star to the K. So you would exactly stop at the very point where the last point lies on the last cylinder. And that's it. You will not blow up more. This procedure stops, terminates at some point because of stability. And so this is what happens to S1. And same thing happens to S2. And eventually, S1 with its chain and S2 with its chain will be glued to each other. And so this is the special fiber of the relative moduli space of ideal shifts of points relative to a divisor inside the surface. So next time I will talk about how to use intersection theory to relate DT invariance of generic fibers of this degenerating family to the DT invariance of pictures like this. And that's the content of Junli's degeneration. Li and Wu, really, degeneration technique. And yes, thank you, and I stop here.
Next time will be when?
Next time, because I'm going to Princeton, next time it will be after April 3rd. Yes. Thanks.
So can one use all this to study Clavia with normal crossing with all this?
Oh, that's an amazing.